麦克风。靠腰，有时候全部录到。
Okay, today continue the lecture about some problems in character acceleration. Number 7 is I will talk about the minimum potential problem. So what potential means? Potential energy can be defined as, for example, if this is B, it is this reference. We call the reference configuration. And how to deform by a loading P. Okay. So this is maybe we also call this is actual configuration. So we define the potential energy is the work you need to do from the actual configuration back to the reference configuration. The work is we call the potential energy system, right? So, so the work is the displacement is opposite to the direction of force. So this is a negative work done by the erosion. So we call this the potential energy. Now, if we want to do so, potential energy contain the strain energy and the work done by external load, internal energy and the external energy of the work, internal work and external work. All right. So before this, I would like to talk about something about the strain energy density. So for example, if this is a specimen, we have a P-loading specimen, right? And each length is L0. Each length is L0, and this is delta L. Okay. The stress is defined as P over A. Zero is we call nominal stress. And the strain is defined for this is delta L over L0. So we can plot a curve for this strain and stress. We have maybe nonlinear material. Okay. Then the area for this is the strain state, and this is the stress. And this shaded area is the strain energy. Right? So you know. So the strain energy is like this area. So this is the absolute. And this is the stress. So the strain energy defined as this times the absolute and equal from the state from zero strain to the current strain. Okay. Current strain, our strain energy. Okay. And if the stress equal to Young's modulus times strain. So this integration will be the strain energy. So it's integration 0 epsilon E epsilon E epsilon. So this is F Then, for the 3D general material, is a work on something work, right? In 3D space. And for any point, you have a strand state. And it's just right. So I sent you some notes yesterday. Okay, you can check. I will number right. You can think about it as for example, this is for epsilon ij, and this is a sigma ij. Okay, for any function, and this is d epsilon ij some quantity. For example, this can be epsilon x, epsilon xy, epsilon xz, epsilon yz, epsilon y, epsilon z. Okay, even 9. Epsilon yx, epsilon zx, 9 terms. And this is corresponding terms. But the similar idea for this, the strand energy density. For the strand energy density, or the strand energy per unit volume. Per unit volume. For the strand energy density, EB and E. So it can be defined as sigma ij, d epsilon ij. And we integrate from 0 to the each instant. Sigma. So this is a strand energy density. The ij here is dummy, so that means sum over. Okay? Sum over. So this can be because if we use a Hooke's law, the sigma ij equal to Cij KL epsilon KL. Hooke's law. Right? So the integration, this constant anyway, this will be Cij KL epsilon ij epsilon. This energy density. Actually, you can write out the epsilon x, epsilon y, or you can write it even here. This is like a sigma x, okay, say 1 1, d epsilon 1 1 plus sigma 1 2, d epsilon 1 2, sigma 1 3, d epsilon 1 3, sigma 2 1, d epsilon 2 1, 2 2, d epsilon 2 2, plus sigma 2 3, d epsilon 2 3 plus items. Okay? So this means items. So if you find strand energy, that will be this one. Right? So yeah, you in 3D. But later on we will use this for just for beam problem. Now a lot of terms of zero. Okay? So this is for general concept. I just recently introduced to you. Okay, so this is the idea of strain energy density. Now, next thing what I'm going to talk to you about is the strain energy in beam theory. Right? So here I need to introduce the strain energy of beams. Okay, the theory I introduced to you is right general. This is a beam cross section, alright? And this is x-axis, okay? And here I have y, and here this cross-section in this position, and here I define an axis which I call the axis. I see this the C axis, and this is eta axis. The C and eta axis are principal represent the principal axis of inertia equal 惯性inertia through the centroid of the cross-section of abstract beam. Okay. That means I give you this cross-section, this prismatic cross-section, and from this one you can find the centroid point O. This is centroid. And you also can find this is a principal axis. Because this is principal axis, I have the relationship is principal axis. That means what? That means for this cross section, the dA, this cross section, is C. For this dA, and this is eta coordinate, and this is the dA moment about the C is the way to find the integration of positions to find the A equal to A times the x bar. X bar is central for instance. But since this principal and we use centroid, so this is 0. Right? We put on centroid. Okay? And also eta dA equal to 0. And most important is this integration. To see eta dA is off diagonal I to xy I to c eta equal to I to c C eta, the term is equal to 0. So this is the principal, the meaning of the principal definition. Okay? It's very important. This term should be 0, right? Okay. So this is the first thing. Once I give you a cross-section, you can find the centroid of this cross-section. And we define this centroid as a point of origin of the point system. Right? And you can find the principal axis. How do I find it? So then you have to find the use the principal eigenvalue problem to find this direction. Alright? Then we define if this is a cross-section and under the loading, because this system under loading of an actual resultant force and some moment, any moment applied on this axis is about the C. Right hand will be this one. Then C. And another moment is equal to rotating about eta axis, whatever axis, and eta. Okay, for B. So N the C, and eta are resultant force. Okay, general force moment. Okay. And the definition is N C is stress times the stress. Okay. Stress times the A is a linear force above this small area. And this force will have a moment about the, you can see is in this way. Should be C. Right, so now every moment, right? So times the pi. Time is eta. This is equal. So this is the resultant moment. Be careful about this definition of moment. Okay? This is the relationship between the resultant moment and stress distribution. It's very important. Okay? 很重要，你猜一句很重要。And the moment about the eta axis is the force, same. But you have a moment arm about this axis is eta. You can see. And integration of the so this definition of the resultant moment about the eta axis. And we also have axial force. There's a sigma in A, and integrate whole area is my actual force. This is from the definition between the mean internal force, the two moments, one actual force. relation with the stress. Okay? Now, if we assume that the fiber stress, very important idea, fiber stress. So we think this is a lot of fiber. Each fiber have a stress, fiber stress. Fiber stress at the point, the C eta. Each point is at the C eta point. The fiber stress, okay, is determined by a linear equation. Okay, not non-linear. Not in this plane is linear. Sigma is A to C plus B eta plus C. So we assume this is a linear relationship between the sigma and the coordinate system. That means this is a stress as a plane. Okay, it's a plane. Okay, plane. Okay, it's supposed to be similar to plane the idea. But this is not the third motion. Okay, assume this. Then I can put this equation to this one, to this one, to this one, to form a relationship for this moment and ABC. So from this, I can solve. So if I input it, then you can solve the, for example, let me show you. The moment, the C equal to the domain, this domain is omega, okay, to the domain omega. Eta A to C plus E eta plus C in A. And this can be equal to A integral the C eta in A plus B eta square in A plus C eta in A. Alright? You can find this term.